let's talk about geometric probability. So, quick recap on theoretical probability, which is how likely an event will occur, and we find it without using data. Remember, it's the number of ways an event can occur divided by the total number of possible outcomes. Geometric probability is a type of theoretical probability, but they give us pictures to help us out. So it can be determined by ratios of length, area, volume, all that good stuff. Now, normally, it can be a little intimidating to look at this at first. Let's take a look at this question. We're given a green circle that's inscribed in a purple circle, and they want to know if I hit this circle somewhere, I know I'm going to guarantee to hit it somewhere. What's the probability that I hit it in the pink region? What's the probability that if I throw like a dart at this figure, and assuming I hit the figure, that I hit it on the pink area? Okay. At first thought, maybe seems a little bit confusing, but luckily we have this picture to help us out. Okay, so it looks like what we're going to need to know is the likelihood of hitting the total figure and the likelihood of hitting the smaller circle. Let me show you what I mean. Okay, so we know that the green circle has a radius of 4 inches, and that can tell us the area of the green circle. Okay, remember, area of a circle is pi r squared, and I know this radius is 4 inches. So the area of this circle is 16 pi inches squared. That's great. What about the area of, let's do this in, I don't have pink, let's do this in blue. The area of the larger circle. So if from here to here is 4 inches, and here to here is 6 inches, then I know that the radius of this larger circle then must be 10 inches. So the area of the pink circle is still pi r squared. I know that my radius is 10 inches. So my area is 100 pi inches squared. Remember, pi is still a number, right? It stands for 3.1415, etc. So to say 100 pi inches squared, we know we're really talking about something like 314 inches squared. Okay, so now I know the area of my large circle. I know the area of my small circle. Okay, so what's the area of this pink space? Well, wouldn't the area of the pink space be equal to the total area minus the area of the small circle? Okay, do you see where I'm getting that? So I have the area of this whole figure, and I'm just subtracting out this part to figure out the area that I have in pink. So my area in pink is again the area of the total, so 100 pi inches squared minus that area of the small circle, 16 pi inches squared. So the area of my pink circle is 84 pi inches squared. That's great, but I haven't figured out a probability yet, right? I wanted to know the probability of randomly picking a point in the pink region. So now I know the area of the pink region, and what's theoretical probability? Remember, theoretical probability is the probability of the likely, or what's the best way to phrase this? So we'll call it the probability of what we want over the outcomes that can occur. Okay, so the probability, I want to hit it somewhere in this 84 pi inches squared of space, right? That's my area in pink. But I could hit it anywhere in that 100 pi inches squared. Okay? So the probability of hitting it in the pink is equal to 84 pi inches squared over 100 pi inches squared. The probability of hitting pink, which is this, comes from my pink real estate area divided by my total area. Okay, so we simplify this. 84 pi inches squared over 100 pi inches squared. Notice that our pi inches squared cancel out, and we're left with 84 over 100, which is 0.84 or 84%. So there's an 84% chance that if I throw a dart at this figure and I know I hit the figure, that I'll hit it in the pink region. Let's practice again. Okay, sorry, I forgot I had this preloaded. Okay, let's do this again. So we have this colored figure here. We have a blue square and a green circle inside it. And we want to know what's the probability, if we know we're going to pick a point on this figure, what's the probability that we pick a green point? So we need to know the probability, or we need to know the space, the area. We need to know the area of the total figure, right? And we need to know the area in green. We need to know the area of the total figure, and we need to know the area in green, because we're going to compare them. We're going to compare the area that we want versus all of the area that we have. So let's start with figuring out the area of this green circle. So the area of the circle equals pi r squared. If the side of the square, if this is 4 feet, then my radius, then this is also my diameter of my circle, which means my radius will be half of it, right? So I'm saying if that's 4 feet, then this diameter must also be 4 feet. And if I cut it in half, I get 2 feet. So my area, 2 feet squared. So the area of my circle is 4 pi foot squared. 4 pi feet squared. Okay. The area of my square, a little easier to find, the area of my square, we know it's just side times side. So if one side, so it's side times side, so if one side is 4 feet, then I know I've got 16 feet squared. 16 feet squared. Okay. So I have a chance of, I have 4 pi feet squared in green, which becomes my numerator, but I could hit anywhere within 15 feet squared, which is my denominator. So this is the real estate on this figure that I want. This is the total real estate that I have, total number of outcomes. Okay, so I simplify this from here. My feet squared cancel out. My 4 and my 16 cancel out. I get pi over 4, which comes out to about 0.79 or 79%. So there's a 79% chance that if I throw something at this figure and I know I hit the figure, that I've hit it in the green region. So we're really just comparing areas, okay? We're taking a ratio of how much the figure in question, so in this case our green circle, we're taking the ratio of that versus the entire figure. Let's do one more example. Okay, so we want to find the probability that a point chosen at random inside the large triangle, so somewhere in this triangle, this big one, what are the chances that if I blindly point at a spot in this large triangle that it also happens to fall in this smaller triangle? So I know I've hit it somewhere in the big triangle. What are the odds that it's also in the small triangle? Okay, so we're going to figure out the ratio of small triangle divided by the ratio of the whole triangle, right? This is what we want, and this is the real estate that we have. So this is what we want, and this is our total. Okay, so we need to figure out our areas. So our area of our small triangle equals 1/2 times base times height. Well, my base in this case is 6 inches, so I get 1/2 times 6 times my height is, let's see, 10. 1/2 times 6 times 10, which is that right? 1/2 times 6 times 10, yes, okay. 1/2 times 60, and 1/2 of 60 is 30. So the area of my smaller triangle is 30 inches. The area of my larger triangle, I'll just draw a large triangle, is also 1/2 base times height. So that's 1/2 times, that base is 9 inches and the height is 15. So 1/2 of 9 times 15, 9 times 15 is 135. So 135 over 2 is the area of my larger triangle. Now I take my ratio. So I'm comparing this little guy to this larger triangle. Okay? So I get 30 inches divided by 135 over 2 inches. So what do I end up with? Well, how do we divide like this again? So we do, this becomes 30 over 1 divided by 135 over 2. Remember, keep, change, flip. This becomes what? 135 divided by 15 is 9. 30 divided by 15 is 2. So I get 2 times 2, which is 4. 1 times 9, which is 9. So I have a 4 in 9 chance of choosing a point on this large triangle that it also falls in the small triangle. So again, remember with theoretical or with geometric probability that it's just a kind of theoretical probability, and you're taking, you can think of it as taking ratios. So anytime they say, what's the probability of being in this region, you take the area of the region that you want and you divide by the total area of your total figure to give you the probability of hitting a point in that region.